Nearly 40 years after a single brief flyby, scientists went back and looked again at data from Voyager 2, and what they found solved a mystery that had confused planetary physicists since the moment the spacecraft's instruments first recorded it. Voyager 2 didn't turn back. It can't. Spacecraft on hyperbolic trajectories don't reverse course, and it's been moving steadily outward for decades. But scientists did turn back to archived readings gathered during a few brief hours in January of 1986, and in doing so, they discovered that the entire flyby had happened during what one researcher described as a genuine cosmic coincidence, an unusual temporary event in space that had quietly distorted nearly everything astronomers thought they understood about the planet Uranus for the following 4 decades. This is the story of what Voyager 2 actually recorded during its historic 1986 encounter with Uranus, why that data confused scientists for nearly 40 years, and what 2 separate recent research efforts have finally revealed was really happening at that distant icy planet during the only close visit any spacecraft has ever paid it. To understand why this particular mystery managed to persist for so long, you first need to understand just how limited our knowledge of Uranus actually is, and why a single flyby, lasting only a matter of hours, has had to carry the entire weight of our scientific understanding of that planet for close to 4 decades. Voyager 2 launched on August 20th, 1977, from Kennedy Space Center in Florida, 16 days before its twin, Voyager 1. Both spacecraft were built for a mission originally expected to last 5 years, focused on flybys of Jupiter and Saturn. But because of a rare alignment of the outer planets that occurs only once every 175 years or so, mission planners realized Voyager 2 could be sent onward to Uranus and Neptune as well, an opportunity that wouldn't come around again for well over a century. Voyager 2 remains, to this day, the only spacecraft in history to have visited either of those 2 distant ice giants up close. Voyager 2 reached Uranus on January 24, 1986, sweeping past the planet in a single, brief encounter, gathering as much data as its instruments could capture during those few critical hours before continuing onward toward Neptune. That flyby produced an enormous amount of genuinely valuable information. The discovery of new moons, new rings, and detailed measurements of the planet's atmosphere and magnetic environment. But it also produced a specific set of readings from Uranus's magnetosphere, the region of space dominated by the planet's own magnetic field that scientists have spent the following decades trying to fully explain. Here's the puzzle scientists have been sitting with since 1986, and why it genuinely didn't add up. Voyager 2's instruments detected something strange about Uranus's radiation belts, the regions where charged particles get trapped and concentrated by a planet's magnetic field. The ion radiation belt at Uranus turned out to be somewhat weaker than scientists had expected, but the electron radiation belt was measured to be extraordinarily intense, with a strength described in NASA's own materials as second only to Jupiter's notoriously powerful radiation belts, the most extreme in the entire solar system. That alone would have been a curious finding on its own. What made it a genuine scientific puzzle was the absence of any obvious source capable of producing that much trapped, energized radiation. Radiation belts typically form and stay charged through an ongoing supply of particles, and at Uranus, its icy moons, which under normal circumstances might be expected to supply a steady source of water-derived ions into the surrounding magnetosphere, were believed to be largely inactive and geologically quiet, offering no obvious explanation for where all that trapped electron radiation was actually coming from. For nearly 4 decades, that mismatch, a surprisingly weak source environment paired with an unexpectedly intense radiation belt, remained one of the more genuinely puzzling open questions in planetary science, made all the more difficult to resolve by the simple fact that Voyager 2's single flyby represented the only direct measurement of Uranus's magnetosphere that had ever been taken, or that was likely to be taken again anytime soon. There was no way to simply go back and gather more data. Everything scientists had to work with was locked inside the readings from that one brief encounter in January of 1986. That changed in 2024, when a research team led by Jamie Jasinski of NASA's Jet Propulsion Laboratory went back and reanalyzed that same archived Voyager 2 data with fresh eyes and found something the original analysis had missed. According to their findings, published in the journal Nature Astronomy, the source of Uranus's puzzling magnetospheric behavior turned out to be, in Jasinski's own words, a cosmic coincidence. In the days immediately before Voyager 2's flyby, Uranus had been struck by an unusual burst of space weather, a compressed, energetic surge in the solar wind that dramatically squashed and compressed the planet's entire magnetic field at almost exactly the moment the spacecraft happened to be passing through. If Voyager 2 had arrived just a few days earlier, it would have observed a completely different magnetosphere at Uranus, Jasinski said directly in NASA's own published statement on the findings. That single insight reframed the entire 40-year-old puzzle. Rather than representing Uranus's normal, everyday magnetospheric behavior, The readings Voyager 2 captured back in 1986 turned out to be a snapshot of the planet caught in an unusual, temporary, and almost accidental state. Its magnetic environment squeezed and disturbed by a passing solar wind event that happened to arrive at almost precisely the wrong, or depending on how you look at it, the most fortuitously revealing possible moment. That 2024 finding explained part of the mystery, the general compression and unusual behavior of Uranus's overall magnetic environment during the flyby. But it left a more specific piece of the puzzle still unresolved. Exactly why the electron radiation belt specifically had been supercharged to such an extreme, near-Jupiter level intensity. Answering that more precise question required a second, separate piece of research, one that built directly on Yashinsky's original insight and pushed it considerably further. That follow-up study was led by Dr. Robert C. Allen, a space physicist and the lead scientist of the Southwest Research Institute's Space Sciences Division, alongside colleagues including Sarah Vines and George Clark. Their findings, published in the journal Geophysical Research Letters, drew a direct, detailed comparison between the conditions Voyager 2 recorded at Uranus in 1986 and a well-documented, intensely studied geomagnetic storm that struck Earth's own magnetosphere in 2019, an event scientists on Earth had been able to observe with the kind of detailed, sustained instrumentation that was never available for the single, brief Uranus flyby. According to Allen's team, the specific phenomenon responsible for supercharging Uranus's electron radiation belt was something called a co-rotating interaction region, a structure that forms when faster-moving streams of solar wind catch up to and slam into slower-moving streams ahead of them, creating a kind of shock wave within the solar wind itself, similar in its underlying physics to how a geomagnetic storm develops here on Earth. When that kind of interaction region strikes a planet's magnetosphere, it can dramatically compress that magnetic field, while simultaneously accelerating electrons already trapped within it, injecting fresh energy into the existing radiation belt, and temporarily boosting its intensity well beyond normal steady-state levels. Allen's team found striking similarities between the specific signatures recorded by Voyager 2 in 1986 and the well-documented behavior of Earth's own magnetosphere during that 2019 storm event, concluding that Uranus's electron radiation belt likely wasn't simply mysteriously intense as a permanent ongoing feature of the planet. It had almost certainly been temporarily supercharged by exactly this kind of passing solar wind structure, arriving at nearly the exact moment Voyager 2 happened to be measuring it. Put both findings together, Yashinsky's 2024 discovery of the broader magnetospheric compression event and Allen's 2025 identification of the specific co-rotating interaction region responsible for supercharging the electron belt itself, and you get a coherent, considerably more satisfying explanation for a puzzle that had confused planetary scientists for nearly 40 years. Uranus's magnetosphere, as measured by Voyager 2 in January of 1986, wasn't showing scientists what that planet's magnetic environment normally looks like. It was showing them a brief, unusual, almost accidental snapshot of the planet caught in the middle of a passing space weather event, one that happened to compress its magnetic field and inject additional energy into its radiation belts at almost precisely the moment the only spacecraft ever sent there happened to be looking. It's worth pausing to genuinely appreciate the significance of that conclusion, because it means an enormous portion of what scientists have believed about Uranus's magnetosphere for nearly 4 decades may not actually describe the planet's typical ordinary state at all. As Allen's team put it directly in their own published statement, this new work explains some of the apparent contradictions in the earlier data and will, in their own words, once again change our view of Uranus. That's a genuinely significant claim, and it's worth being precise about exactly what it means. It doesn't mean Voyager 2's original measurements were wrong, or that the spacecraft malfunctioned in some way. It means the specific moment in time that spacecraft happened to fly through turned out to be an unusual, temporarily disturbed one, rather than a representative, everyday sample of what Uranus's magnetic environment generally looks like, a distinction that matters enormously for anyone trying to build an accurate general model of how that planet's magnetosphere actually behaves under normal, undisturbed conditions. There's a broader lesson embedded in how this particular mystery finally got resolved, one that connects directly to a recurring theme running through much of modern planetary science. Sometimes, the most valuable scientific progress doesn't come from launching a brand new mission or gathering fresh data at all. It comes from returning to data that's already been sitting in an archive for decades, and looking at it again with new tools, new comparative context, and new questions in mind. Neither Yashinsky's team nor Allen's team needed to send anything new to Uranus to make these discoveries. They needed to go back, carefully, methodically, to readings gathered during a few brief hours in January of 1986, and examine them with the benefit of nearly 40 additional years of accumulated knowledge about how solar wind, magnetospheres, and radiation belts actually behave, knowledge built substantially from decades of much more detailed, sustained study of Earth's own magnetic environment. That connects to a genuinely pressing practical concern within the broader planetary science community, one that gives this entire story real, forward-looking significance beyond simply correcting an old misunderstanding. The National Academy's 2023 Planetary Science and Astrobiology Decadal Survey, the document that guides NASA's long-term mission priorities, specifically identified Uranus as a priority target for a future dedicated mission, precisely because our understanding of that planet remains so heavily dependent on a single, brief, decades-old flyby. If Voyager 2's original 1986 measurements really were distorted by an unusual temporary space weather event, as this newer research strongly suggests, that has direct practical implications for how mission planners and scientists should interpret everything we currently believe we know about Uranus's magnetosphere, and for what kind of sustained, repeated observation any future mission to that planet would actually need to prioritize in order to finally capture a genuinely representative, undistorted picture of how that ice giant's magnetic environment behaves under normal, ordinary conditions, rather than during one unusual, accidentally significant afternoon in January of 1986. While all of this historical reanalysis has been unfolding, it's worth connecting it back to what Voyager 2 itself, the actual spacecraft, is doing right now in 2026, because the same machine responsible for gathering that decades-old, newly reinterpreted data is still out there, still transmitting, and still very much part of an active, ongoing mission. Voyager 2 crossed the heliopause, the boundary marking the true edge of our solar system, in November of 2018, becoming only the second human-made object in history to reach interstellar space, following its twin Voyager 1, which had crossed the same kind of boundary 6 years earlier. Since then, Voyager 2 has continued transmitting data from beyond the solar system's protective bubble, using instruments that have helped confirm and refine scientists' understanding of that boundary in ways its twin alone couldn't achieve. Both Voyager spacecraft now face the same fundamental limitation: a radioisotope thermoelectric generator that converts the heat from decaying plutonium into electricity, losing roughly 4 watts of available power every single year, with no possibility of refueling or replacement. On April 17, 2026, NASA engineers made the difficult decision to permanently shut down Voyager 1's low-energy charged particles instrument, a device that had operated almost continuously since the spacecraft's 1977 launch in order to conserve its rapidly dwindling power supply. Voyager 2 currently has 3 functioning science instruments remaining: its cosmic ray subsystem, its magnetometer, and its plasma wave subsystem, one more than its twin, thanks to Voyager 2 currently retaining a slightly larger power margin. That slightly larger margin is precisely why NASA engineers chose Voyager 2 as the test subject for an experimental power recovery procedure nicknamed internally the Big Bang, designed to shut off a group of powered heating elements simultaneously and activate lower power alternatives instead, squeezing additional operational time out of each spacecraft's fading power supply. According to NASA's own published plans, that procedure was scheduled for testing on Voyager 2 during May and June of 2026, with the same fix planned for attempt on Voyager 1 no earlier than July, if the Voyager 2 test succeeded. If the plan works as hoped, NASA has indicated there's even a possibility that Voyager 1's shutdown instrument could eventually be switched back on, buying both aging spacecraft, additional time to keep gathering data from the increasingly distant, increasingly unfamiliar regions of interstellar space they continue moving through. There's something genuinely fitting about the fact that Voyager 2, the same spacecraft whose 40-year-old Uranus data just yielded a major new scientific insight through careful reanalysis, is also currently serving as the test bed for keeping the entire Voyager mission alive a little longer, into whatever additional discoveries might still be waiting in its ongoing stream of interstellar data. It's a spacecraft that has already given scientists more than anyone in 1977 could reasonably have expected, first through its historic flybys of all 4 giant planets, then through its unprecedented direct measurements of the boundary between our solar system and interstellar space, and now, decades later, through data that's still yielding meaningful new discoveries, simply because researchers took the time to look at old readings with fresh eyes and better comparative tools. It's worth being precise one final time about what actually happened here, since that precision matters more than any dramatic framing built around it. Voyager 2 didn't turn back, and it didn't detect anything new during some recent maneuver. What happened is that scientists turned back to data the spacecraft gathered nearly 40 years ago, and in doing so, uncovered evidence that an entire planet's magnetic environment had been temporarily, dramatically altered by a passing solar wind event at almost precisely the moment humanity's only spacecraft ever sent. There happened to be measuring it. That's not a lesser story for being grounded in careful, patient reanalysis rather than a single dramatic new observation. If anything, it's a more genuinely satisfying one, a reminder that even data collected decades ago from a machine that flew past its target for only a few brief hours before, continuing on its way, can still hold answers that take the scientific community most of a human lifetime to fully recognize and understand. Uranus sits out there right now, roughly 8 billion miles from the Sun, its true ordinary magnetosphere, still not fully directly measured by anything other than that single briefly disturbed snapshot from January of 1986. Whatever a future dedicated mission eventually reveals about what that planet's magnetic environment actually looks like under normal, undisturbed conditions, the groundwork for understanding it correctly has already been laid, not by a new spacecraft, but by scientists willing to look one more time at data that had been sitting quietly in an archive for nearly 40 years, waiting for someone to finally notice what it was actually showing them all along. If you want to follow how this reinterpretation continues to shape plans for a possible future mission to Uranus, and how Voyager 2 itself continues its ongoing journey through interstellar space, that story is still very much unfolding right now. Subscribe if you'd like to keep following where it goes.